Before we get started, I'd just like to, I'm going to give you a little assignment for throughout the course of the lecture today. So what I'd like you to do is write down at least one question you have either about what we've talked about or some other topic in convection. You can write it in Spanish and Dave can translate the questions for me. But I'd kind of like to see sort of and if you want to tell me what you're interested in, what your interests are, that could be another thing too, just so that we have a little bit of feedback about what everyone in here is kind of, why they're interested in convection, and maybe use that as kind of a platform for subsequent discussions and connecting people. So, all right. So we'll check, as everyone leaves the door, we'll make you hand us the paper. Okay? So today what we're going to do is talk about the topic of how convection in the tropics is coupled to larger scales. And this, as we kind of mentioned at the outset of this course, obviously there are many things we can talk about in the study of tropical convection, and we kind of chose topics obviously based on the interests that Kathleen, Dave, and I have. And the coupling between convection and the large scales is something that's of particular interest to me. It's actually how I first became interested in studying the tropics with the first topic. And you'll notice here I'm using some Spanish, El Nino. The El Nino Southern Oscillation, and in particular, when I first began working, I was looking at how ENSO, which we kind of understand as a phenomenon that's, the center of action of ENSO is in the Pacific, but we know that ENSO has impacts on climate outside of the Pacific. We see those impacts in high latitudes, but we see them in the tropics. And so I was focusing on understanding this, what we call tropical teleconnections. So I'll spend quite a bit of time developing that. And then from there, kind of going back in the direction of theory, to talk about a kind of way of looking at the tropics which leverages on the so-called weak temperature gradient approximation. And this essentially follows from, the observed behavior of temperature, at least away from the surface in the tropics, that it's a relatively uniform, horizontally uniform field, and we can actually get a lot of mileage out of that. And that actually connects nicely back to what we were talking about yesterday in terms of convective quasi-equilibrium. So we'll kind of review that. Then I want to take you through the development of what are really a family of models, quasi-equilibrium tropical circulation models. Is just an example. I mean, the focus of today isn't about modeling, but this type of model, which is called an intermediate level complexity model, is a sufficiently simple model. I mean, it's complex enough that you still run it numerically, but it's sufficiently simple in a sense that you can kind of think of it as theory, just theory that you have to run numerically. So I'll kind of talk about that. And then finish up with another topic that I've worked on, which is kind of related to the spatial transitions, what we called convective margins in the work that we did, sort of understand things from a more spatial perspective. Okay? So what do things currently look like in the Pacific, since I want to talk about El Nino teleconnections? No one's laughing at this little cartoon. This cartoon from the LA Times back in late August illustrated what was, at the time, the developing El Nino, which I think Mike McFadden maybe was the person that came up with the term Godzilla El Nino. And also at the time, there was kind of an interesting phenomenon happening with kind of warm water at higher latitudes, which was called the blob. And so back in August, we were kind of thinking about El Nino, Godzilla El Nino versus the blob. And, there's a palm tree. So this was, thinking about what would happen in Southern California when these two titans of the climate system collide. But what I want to focus on is the El Nino side of things. So these are relatively current conditions in the tropical Pacific. So this is the the observed sea surface temperature, so in degrees C, but the departures from the mean sea surface temperature over this 7-day period from just centered on January 20th. And what it shows here is the anomalous warm sea surface temperatures across both the central and the eastern Pacific, with amplitudes on the order, here in this part, maybe 3 to 4 degrees C above normal. So this is certainly, living up to its reputation as, very powerful El Nino. As you might imagine, and we'll talk more at length about this, having anomalous, such an anomalous departure of the surface conditions in this part of the Pacific has a big impact on the atmosphere and a big impact on convection. And in turn, as we'll see, that impact on convection in the Pacific is then felt elsewhere in the tropics and at higher latitudes. And this is kind of related to that is anomalies in outgoing long-wave radiation. So you can think of this as what's being illustrated here, departures from the mean outgoing long-wave radiation in watts per meter squared. And where it's negative, it's essentially showing you where there are very high cold cloud tops. And so you're kind of seeing that sort of in this part of the Pacific, kind of where we have the warm sea surface temperatures, that you have this departure suggesting that you have the development of anomalously intense convection there, which is growing these deep convective clouds. And you see also then, if you look, getting to sort of the remote aspects of the interaction or the connection, you see these kind of large departures elsewhere. And, obviously, whether or not they're connected depends on, having a kind of dynamical understanding, a thermodynamic understanding of what's going on. There's a tendency, we see this a lot in the United States, maybe it's similar here in Mexico, that when we have a large El Nino event or a La Nina event, there's a tendency to blame things on El Nino. This was from a Wall Street Journal article in early January. El Nino-driven storms bring high winds to California, heavy snow to Arizona. When we look at the statistics of rainfall on the west coast of the U.S., we do see a fairly convincing relationship between El Nino conditions and anomalous, positive anomalies in rainfall over California. But I also pulled this headline talking about the storm that I suffered through this past weekend. So now the practice has come, just like with hurricanes, that we give significant winter storms names. So Winter Storm Jonas dumped 60 centimeters of snow on my house. And so, the question that now people are asking is, well, what role did El Nino have in the occurrence of this particular event? There's a tendency, I think, in the media to do this, to want to draw connections. I would caution, I'd have more confidence in this type of connection than I would have in this one, just because, on the one hand, with El Nino, we're dealing with a climate phenomenon. With a snowstorm, it's inherently a weather scale phenomenon, and there's lots of things that can contribute to weather. So just a caution. But also, these El Nino events, big El Nino events, tend to inspire people to make little cartoons. So here's one that happened that was published in a paper back in 1990, probably the winter of 97 or 98. 98, I guess, talking about, 1990s, the winter 1997 into 1998, there was a big El Nino event. That was the first year that I was in California, and my impression of what California's climate was like after that first year was very different than what I experienced subsequent to that, because we had a lot of rainfall. At times of the year which I discovered later, it shouldn't be raining, like in June. So, the cartoon here, there's a little vase on the desk or something that was broken, and so the mom is saying, who broke the vase? The kid says, it's El Nino's fault. My son hasn't yet discovered this, but I'm sure he will blame El Nino. But then the next year, the vase gets broken, and now it's La Nina's fault. So it's kind of the same action, but blamed on two different things. And then this one I like just because you can't actually read this, but this is freeway signs from Southern California, Malibu, Los Angeles, Burbank. And there's some large creature here that's crawled out of the sea, and a person in the car says, I'm starting to get really nervous about this El Nino. And we kind of laugh about this, but again, going back to the first winter I was in California, people would call into local radio stations or television stations saying, this really strange looking fish has washed up on the beach. And, the sea surface temperature off of San Francisco was at the peak, I think, 3 degrees C, maybe even more, 4 degrees C above normal. So fish, maybe migrating from along the coast of Mexico, had basically followed the warm water up the California coast and was making people scared. Nothing like this, although we're still in this El Nino, so who knows what will happen. So what I would like to talk about is the ENSO-tropical teleconnection. So obviously, when we talk about ENSO, we start in the Pacific, and these cartoons are probably well known to most of you, kind of illustrating what the normal state of things looks like in the Pacific. And I'll talk a little bit more about this cartoon picture, but we have this sea surface temperature gradient along the equator with relatively cold sea surface temperature in the eastern Pacific and a warm sea surface temperature in the western Pacific. Co-located with that warm sea surface temperature in the western Pacific, we tend to see intense deep convection with deep towering cumulus clouds that go all the way up to the tropopause and even sometimes punch through into the stratosphere. Very much different than what we see on the eastern side of the basin, co-located with this cold sea surface temperature where we essentially have no deep convective cloudiness like this, or very little, under sort of normal conditions. During El Nino conditions, thinking back to that anomalous sea surface temperature map that we looked at for the current state of affairs, when you have the warm sea surface temperature here in the west, in the east, or the central part of the basin, it encourages the development of convection further to the east of what we would normally see. Okay? And just to kind of orient you, again, it's probably something that you're pretty much familiar with. Actually, I think I changed this slide slightly, so the green box here is a little bit off, but we measure the El Nino Southern Oscillation. We can measure it a number of ways. A common way is to look in terms of the sea surface temperature averaged over some box. And this particular one is called Nino 3.4, but there's Nino 3, there's Nino 1, Nino 1 plus 2, so on and so forth. And they're all just different variations on the same theme. But it essentially shows you the departures of sea surface temperature from some climatology, and showing you these kind of ups and downs that happen on interannual timescales. It's irregular, although if you look at the power spectrum of this, you'll see kind of a broad hump in the sort of interannual timescales from 2 to 7 years or so, with some lower frequency modulation as well. But just to point out, the 1997-98 event, which came to be known as the El Nino of the century, the El Nino of the last century now, was this thing. And many people got interested in the study of El Nino because of the big event that happened in 82, 83, but this is the current Godzilla El Nino. Indications are that it's probably at its peak or slightly past its peak, but there's a lot of damage still to be done. So ENSO fundamentally involves the intensification, I should say this. People tend to emphasize the spatial redistribution of rainfall in the Pacific as you kind of shift rainfall from west to east, but also an overall intensification of rainfall in the Pacific, and I'll kind of come back to that point. But what I was interested in when I first started looking at this are the implications of this kind of change in convection in the Pacific for climate elsewhere in the tropics. So lots of words on this slide, which I'm sorry for, but it's essentially to ask the question, who's driving the Pacific? So we have both the ocean and the atmosphere to consider. So the first possibility is that the ocean is the driver of what's going on in the Pacific. And the way this kind of argument would go We have the tropical Pacific having a very pronounced zonal asymmetry in SST, with it being warm in the west and cold in the east, relatively speaking. The intense deep convection is favored over the warmest water in the west. With the occurrence of intense deep convection in the west, in terms of the sort of, circulation, there's associated ascent. You have, again, thinking about convection from kind of the parcel view, you have lots of air masses that are rising up in the atmosphere, leading to or related to low-level convergence of the flow, of the horizontal flow, and relatively low surface pressure. In contrast to the east, where we have descent, and again, this is kind of thinking about things in terms of the normal state of the Pacific, low-level divergence and high surface pressure. So as a result of this pressure difference, this zonal pressure difference between the west and the east, there's an easterly flow, the wind stress or the wind blowing along the equator is directed from east to west. So, in this kind of view that the ocean is the driver, it kind of starts from the SST distribution. The other, I don't know, are there any oceanographers in the audience? Okay, there's one. Most of the rest of us, we know, of course, that the atmosphere is more important. Just kidding. No, the atmosphere is the driver. So we could take this view. And in this view, it essentially starts with the winds. So we have an easterly wind stress that's applied to the ocean surface. So that, again, that wind that's blowing from east to west leads to changes within the ocean itself. In particular, there's a structure within the ocean that separates the upper, more mixed part of the ocean from the more stratified part below, which is called the thermocline. And if you look at the location of the thermocline within the vertical depth of the ocean, it's tilted. So there's a shoaling or a shallower thermocline in the east, deeper thermocline in the west. Also in the east, we tend to see upwelling, and I'll make a little note about that in a second. But these conditions of having a shallow thermocline and upwelling conditions in the eastern Pacific would be associated then with the occurrence of cool sea surface temperature in the eastern Pacific. By contrast, in the west, where there's a deep thermocline and essentially no upwelling, we'd have warm sea surface temperature. Now, the aside here is to really understand this, we need to think about differences in the ocean dynamics and the currents kind of interacting with the boundaries, the eastern and western margins of the Pacific, and how essentially the vorticity budget of the ocean kind of looks different on both the east and west sides. That's not really important. It's just to say that in this view, we'd start from the winds and kind of get to the SST. So it's clear, when you kind of think about things, this is circular, right? There's no reason we should start with the winds, or a priori, no reason to start with the winds, no reason to start with the sea surface temperature. Then in fact, we really have to understand the mean state of the Pacific as a coupled ocean-atmosphere system. And this coupling between the ocean and the atmosphere as it pertains to kind of our understanding of this large-scale climate of the Pacific is known as the Bjerknes feedback. Okay? Feedback here implies that if you perturb, if you introduce some kind of perturbation into the system, it's going to, if it's a positive feedback, it'll amplify. If it's a negative feedback, it'll damp. And so, you can kind of think then that the mean state is kind of in this Bjerknes feedback mode, and then ENSO is kind of a perturbation on top of that Bjerknes feedback. So getting back to the teleconnections more specifically, this is also a very common sort of cartoon that you see that kind of addresses these teleconnections. And again, teleconnection is just a word we use for some impact that's remote. You have some forcing happening somewhere, you have a remote impact, we call that a teleconnection. So on the left-hand side is the El Nino phase. This is when we have warm sea surface temperatures in the eastern or central Pacific, and the right-hand side is the La Nina phase. And you see these kind of characteristic, and this kind of goes back to work from the 1980s by Ropolewski and Halpert and others, kind of identifying these sort of characteristic places, both in the tropics and in higher latitudes, where we sort of see these signatures in terms of, for example, being relatively warm and wet in this part of the Pacific, this kind of horseshoe shape region of relatively dry conditions in the western Pacific, a kind of well-known teleconnection over northeastern South America, particularly in the Nordeste region of Brazil, with relatively dry conditions during El Niño. And then more or less the mirror, the sort of opposite picture during La Nina, although, it's a little bit more complicated than that. In terms of, North America, or the higher latitudes in North America, you kind of see the sort of characteristic of wetter conditions over particularly over southern California, wetter and cool conditions over the southeastern U.S., and sort of, then in the La Nina phase, the wetter conditions on the west coast of the U.S. kind of shift northward. One of the things you'll often see is, so a question you might ask is, okay, these are sort of the signatures that we observe. How do we really understand what's going on in terms of the dynamics and the thermodynamics? And just one more point here, coming back to the current conditions. So this was a forecast, can't quite remember when this forecast was produced, relatively recently, kind of looking at what we might expect, running a model and kind of looking at what we might expect in terms of rainfall, the expectation for rainfall conditions during March, April, and May. And so you can see, even if we have this Godzilla kind of going back underneath the ocean where Godzilla comes from, disappearing, but it still has this kind of residual warm sea surface temperature with the likelihood of above normal rainfall, kind of persisting through March, April, and May. You see that kind of horseshoe-shaped pattern of dry conditions to the north, to the northwest and the southwest, maybe wetter than normal over Australia. Here, the kind of dry conditions over Nordeste, but also extending back over the Atlantic. Kind of in this little box of interest for many people in this room, or maybe slightly to the north, it kind of looks at sort of the scale of this model, and I don't remember what resolution this is, but you see generally wetter conditions, or the prediction for above normal rainfall conditions. But if you take a more regional perspective, you can actually see that there's quite a bit of regional structure, so I apologize that not more of Mexico is shown, but certainly in Central America into Colombia, this kind of prediction, and I don't actually remember what the source of this is, but is actually suggesting drier than normal conditions through from December through March, maybe wetter than normal conditions in the Yucatan, which might be more in line with what this global resolution or this global numerical weather or prediction model is suggesting. So that's kind of a caveat that we kind of look at these structures oftentimes in a very large scale sense, but there's a lot of regional flavor to it as well. And certainly, from the point of view of, say, the societal impact, you would certainly want to know what's happening in your neighborhood. The kind of global picture might be fun to look at, but the impacts happen locally. So I want to turn to the kind of work that we did. Oh, that looks really bad. But this is to look at observed climate signals outside of the Pacific, and this, for later reference, this is what we'll refer to as the remote tropics. So the remote tropics, for our purposes here, is this green box. And what's plotted on the left-hand side is March, April, May sea surface temperature for grid points over the ocean from a particular product INSEP sea surface temperature, and for land grid points over here. So March, April, May of 1998, that was a few, a season or so kind of after the peak of the 97-98 event. You still see lots of residual warming, particularly right up against the coast of South America, but also kind of pervasive warming of the remote tropical ocean and also the remote tropical land surface, on the order of 1 to 3 Kelvin for the land, and on the order of 1 Kelvin or so for the ocean. In terms of precipitation, and again, sorry for the kind of crappy image here, red here actually means above or anomalously positive rainfall, and blue is anomalously negative. So again, you kind of have the co-located with this warm sea surface temperature above normal rainfall and then below normal rainfall here. But then in the remote tropics, a tendency, and a kind of a widespread or coarse sort of view of below normal rainfall, although some regional, obviously regional differences. So, for example, the Western Indian Ocean had, over this time period, kind of centered on the El Nino event, actually above normal rainfall. But over South America, maybe equatorial Africa, and the eastern part of the Indian Ocean into the far western Pacific, you actually had above normal rainfall, below normal rainfall. So what I was interested in doing is kind of looking at this at sort of the largest scale, and that's to compare what's happening over the tropical Pacific, kind of taking a big box over the sort of ENSO center of action in the Pacific, and contrasting that to the remote tropics. And I was focusing in particular on rainfall. So the observations here, and this is actually, I've drawn a line through here. This is actually a significant correlation for this observational data set, and I think it was probably, well, at the time that would have been about 25 or 26 years. I mean, marginally statistically significant, but kind of suggesting that if you plot the, so this is actually for the remote tropics on this axis, right? The remote tropical precipitation anomaly, so averaged over that green box from the slide before, plot that against the average precipitation anomaly in the tropical Pacific, and there's this negative relationship between them. So if the Pacific over in this kind of large box average is above normal rainfall, the remote tropics is below normal and vice versa. And then some models kind of showing, maybe the models have a stronger tendency to have that anti-phasing. I'll talk more about this particular model, which has a really tight negative correlation, but a more realistic, perhaps, climate model also had a pretty strong anti-correlation. So how do we, so again, more rainfall over the Pacific during El Nino, corresponding to less rainfall elsewhere in the tropics. So how do we understand this kind of large-scale anti-phasing between the Pacific and the remote tropics? And I would just kind of point out here, I don't think anyone has actually looked at this kind of diagnostic in, say, the current CMIP-5 models to actually see if you kind of aggregate over these large scales how this anti-correlation looks. So someone out there who wants to look at the CMIP-5 models and do this might be a kind of low-hanging fruit that you might want to take a look at. So how do we explain this? Well, I mean, there's been sort of at least a conceptual model or certainly qualitative, even semi-quantitative model, which is actually attributed to Gill, 1980. And I had originally meant, if you look at the syllabus online, to talk about the shallow water equations, but turns out there's just not enough time. Having said that, the Gill model is kind of a model built on this shallow water equation framework. And essentially what we do, or what's done in a Gill model, is to introduce some source of a perturbation somewhere into the model. So you construct the model with some mean state that you give it, and you impose some perturbation on top of that mean state. And the Gill model then is solving for the perturbation relative to whatever mean you give it. And in particular, for this application to El Nino, we impose a heating anomaly. Okay, so the effect of convection on the atmosphere, and I think we'll kind of talk a little bit more about the details of this tomorrow, but convection heats the net result of deep convection is to heat the atmosphere locally around it in the free troposphere. And so that's the sort of thing, the imposed diabatic heating anomaly in the Gill model for the El Nino case would correspond to this anomalous convection over the warm sea surface temperature. So that's kind of the forcing. And then the model can be used to solve for the response of the dynamics. And an important thing here is this is a dry dynamical model. So it's actually not, it doesn't have convection in it, but we're representing the effect of convection through this imposed forcing. So then we can look at what the solution to the Gill model looks like, a steady state solution, if we kind of keep the heating fixed. And what you get here is shown in these diagrams. So the top panel here is an indication of the vertical motion field. It's actually what's being plotted here is the negative pressure velocity. So pressure velocity, ascending motion corresponds to negative omega, but it's the negative of that. So where you see positive contours corresponds to ascending motion. And so you see these kind of closed contours. That's essentially where the heating anomaly is centered. It's a Gaussian heating anomaly that's centered on 0, 0. So kind of co-located with where you have the Gaussian heating anomaly, diabatic heating anomaly, you see the kind of circulation is responding with large-scale ascent. Outside of that, and it's kind of hard to make out, you can see two closed contours here, but essentially everywhere else in the domain outside of that kind of Gaussian perturbation, you have sinking motion, okay? And a simple kind of explanation for this is that you have this kind of domain that has a fixed amount of mass in it. You have some of the mass that's going up here, right? If you want to conserve mass in the domain, you have to have mass sinking elsewhere. So it's kind of what goes up comes down, but it's stuff going up here is coming, the mass that's going up here is coming down elsewhere. This is what the surface pressure field looks like, and also the surface wind field. And you know, what's interesting about this is the structure of the surface pressure field has a very characteristic looking pattern. I often think it looks kind of like a bird, like a duck. You know, here's the beak and here's the eyes. But we can kind of look at this, and from our understanding of wave dynamics in the tropics, we sort of understand what this structure is. This part of it corresponds to what we call a Kelvin wave, kind of the part off to the east of the heating anomaly, and this kind of this sort of couplet corresponds to a Rossby wave, in this case stationary Kelvin wave and stationary Rossby wave, that kind of give it this characteristic spatial structure. And then the vertical motion field, just to emphasize what I was saying above, co-located with the heating anomaly, or the center of the heating anomalies, where we have the strongest rising motion, and then the kind of streamlines here showing the sinking motion that's happening elsewhere. Okay, so this is the sort of conceptual, and again, it's a model, qualitative in the sense that we can sort of think here, again, no convection in the model per se, but you can imagine that here where you have the ascending motion, which we've put there because we attribute it to convection, but outside of that convecting region, we have sinking motion. If we look in the real atmosphere, where we tend to see large-scale subsidence is places where we don't have deep convection. Okay, so there's kind of the qualitative argument then is where we have this anomalous subsidence or anomalous sinking of air, you're essentially suppressing convection relative to what it would normally be. And so that's kind of the idea that people sometimes refer to this as the anomalous Walker circulation, that you're just kind of developing this circulation that because it's sinking outside of the sort of ENSO region, it's suppressing the convection. And that's kind of consistent with the picture I was trying to argue, that you have this anti-phasing, right? So there's nothing really new here per se, but the part that is new really came about through some work in the early 2000s. This is it's probably been cited 500 times, maybe more, paper by John Chang and Adam Sobel that wanted to recast the problem of the ENSO tropical teleconnection in terms of tropospheric temperature. Now, why did they want to do this? Well, the Gill model is essentially a dynamical construct, and the way it was designed by Gill, it's a dry dynamical model, so it doesn't have moist processes in it. But we know that the teleconnection has an impact on rainfall, so it has an impact on moist processes in the atmosphere. So intimately, the teleconnection is also a problem of thermodynamics. The Gill model emphasizes the dynamics. The teleconnection also involves dynamics. Now, it turns out, separating dynamics and thermodynamics in the tropics is maybe not that straightforward. We tend to see them kind of tightly coupled. But the idea behind this Chang and Sobel 2002 paper was really to kind of look at things from the thermodynamic side, which hadn't been really done before. They were kind of motivated in doing this by looking at the temperature field in the tropics, and I'll come back to this point a little bit later, but essentially if you look at the tropospheric temperature, these are correlation plots that are derived from microwave sounding or microwave retrievals of tropospheric temperature above the boundary layer. I mean, it's some deep tropospheric average temperature above the boundary layer. And what they did was to correlate the sea surface temperature in this green box, the NINO 3 region, kind of one of our canonical measures of ENSO, correlate that with the tropospheric temperature in this deep layer in the troposphere up above. And what you find, so this is the sort of contemporaneous correlation. These are for monthly means. So you have, as you might expect, where you have this anomalous convection, it's developing a strong correlation with the temperature up above. Anomalous convection heats the free troposphere up above, giving you a positive correlation. If you go forward in time, so if tropospheric temperature lags NINO 3 by 2 months, so in other words, if you take the NINO 3 sea surface temperature, say in the month of December, and you correlate that with the tropospheric temperature the following February, so you just shift the tropospheric temperature time series by 2 months relative to sea surface temperature, then you can actually see that kind of region, red here, corresponds to a very strong, statistically significant correlation. That's now extending over much of the tropics. 4 months, maybe even more pronounced, that you basically have this warming, this anomalous warming of the free troposphere in the tropics kind of everywhere, longitudinally, and kind of filling the region between roughly 20 south and 20 north. I mean, it's a little bit narrower over here, but there's a very broad region in the deep tropics that's very strongly correlated with the sea surface temperature in the NINO region. So this is kind of a schematic to illustrate, how this mechanism that was proposed in the 2002 paper, what's become known as the TT, or tropospheric temperature mechanism, how it's actually pictured to work. So you start with the warm sea surface temperature boundary condition in the Pacific. That induces it's associated with anomalous convection in the atmosphere up above. That anomalous convection would locally heat the troposphere around it. Then significantly, and this is the part in a sense we can see from the Gill model, that this warming anomaly locally is propagated through the effect of wave dynamics in the tropics, and propagated relatively quickly across the entire tropical belt. Okay? Now what happens in the remote tropics? We've warmed up the free troposphere in the remote tropics, and then thinking back to what we talked about yesterday in terms of convective quasi-equilibrium, and I went through this kind of derivation at the end, showing that the relationship between the thickness in the free troposphere, which is by the hypsometric equation, is kind of related to how warm that layer is, that's in turn coupled to theta E in the boundary layer. So you can kind of think, as the free troposphere warms, if convective quasi-equilibrium holds, then you would expect theta E in the boundary layer to go up. And then in terms of, say, the warming of the ocean itself, because theta E in the boundary layer is coupled to sea surface temperature through surface fluxes, you can kind of get the communication of the temperature signal downward from the free troposphere through the boundary layer into the ocean. Now, I point out here, of course, that the linkage here is convective quasi-equilibrium, which we talked about yesterday. What's kind of interesting about this is Chang and Sobel kind of applied this mechanism, but really with sort of the ocean in mind, okay? There's a question about, does this really work? Does the same mechanism work over the land surface? And that's actually a question that hasn't really been addressed. And I think partly it hasn't been addressed because we're really only scratching the surface in terms of how to think about convection over the land surface. Much of our understanding of convection in the tropics, I think I mentioned the point yesterday, much of our understanding of convection in the tropics is kind of built on how we understand convection over the ocean in the tropics. But as we talked about on the first day, the land surface is fundamentally different in terms of, for example, having a strong boundary layer, a strong diurnal cycle, which we don't see over the ocean, or we see a much attenuated diurnal cycle over the ocean. So actually, this is kind of an area, I think, how the teleconnection works over the land surface that's still kind of an outstanding challenge. Although, you know, I say that, but I think a lot of people think the teleconnection problem is solved. So I guess my perspective is that it's not really solved because we don't yet know how it works over the land. I have a student who's working on that, so hopefully in a few years he'll figure out the answer. So I want to turn, I spent quite a bit of time developing the tropical teleconnection, maybe reviewing things for most of you, I don't know, but kind of turning back to a more theoretical kind of perspective to think about some basic considerations of our understanding of the tropics vis-a-vis mid-latitudes. So in mid-latitudes, we have this kind of idea, if you haven't heard of quasi-geostrophy, you've probably heard of geostrophy, a kind of idea that we can develop our understanding of dynamics in the mid-latitudes or high latitudes in terms of a kind of balanced dynamical picture, okay? And the common picture is, well, the sort of first order picture is the geostrophic balance, essentially the balance that obtains between pressure gradients and Coriolis. Quasi-geostrophic is kind of a deviation from that, but it provides a pretty good picture of what's going on. So in particular, the sort of quasi-geostrophic balance leads to things, processes, baroclinic and barotropic conversion processes that we observe in the mid-latitudes. The important point here, in a sense, is that these processes, which are kind of, sort of dynamical, thermodynamic as well, but these are kind of related to the sort of basic equations, if you will. The sort of physics, in a sense, through the diabatic heating, the effect of radiation, convection, surface fluxes, those are obviously important, but these other processes, particularly baroclinic conversion processes, are typically dominant, okay? If we're talking about the evolution of the atmosphere on daily timescales. So what is all of that really saying? Well, if you look at a map of the weather over mid-latitudes, you'll see structures like fronts, right? A front is kind of an example of a baroclinic process. And even from the earliest days of meteorology, when we didn't have the mathematical tools to understand how fronts move, we had a qualitative picture of how they move. Meteorology began as a descriptive science. So for example, if you see a front kind of draped over the west coast of the US, in a few days, barring something going wrong, that front's going to be over the eastern US. So you can kind of understand that, and that's really as a result of this, okay? In the tropics, things are quite different. So baroclinic instability, in a nutshell, is related to having strong temperature gradients. Baroclinic instability is typically not very important. I say this in the sense of large scale. You could have more local scale things in which baroclinic instability, where you might have locally large temperature gradients that are more important, but in the kind of largest scale sense, that's not important. And so the upshot of that is that these other processes, diabatic heating processes, are more important, relatively speaking, in the tropics. And that makes the problem harder in a sense because we don't have kind of that sort of descriptive understanding like we do in the mid-latitudes. And I would also point out that if you're within 5 degrees of the equator, so what people sometimes refer to as the deep tropics, there's no hope of geostrophic balance holding. The Coriolis parameter associated with the rotation of the Earth and the spherical geometry, Coriolis parameter vanishes at the equator. And so if you're right on the equator, there's no way you can balance the pressure gradient force with the Coriolis. Okay, so there has to be some other balance. Other types of balances, you might have a nonlinear kind of balance, and because it's nonlinear, it's much more complicated. So in the deep tropics, that really makes things fundamentally different there. So what I want to focus on is an idea called the weak temperature gradient approximation. And essentially, the weak temperature gradient approximation, we can say we have a small Coriolis parameter near the equator. We have efficient equatorial wave dynamics of various kinds. And as a result of these things, horizontal temperature gradients at least in the tropical free troposphere, tend to be quite small. In other words, if you move from point to point in the free troposphere far enough away from the surface, really if you get above, say, 850 millibars, you're good enough. If you move anywhere, and obviously you don't hit the Tibetan Plateau or something, you're going to see relatively small horizontal temperature gradients. It turns out we can exploit the weakness of tropical temperature gradients to give us some sort of dynamics, a kind of balanced dynamics, if you will, and relate those to diabatic processes, in particular convection. So, yeah, we can take advantage of this balanced dynamical framework, which we call the weak temperature gradient approximation, to understand something about the tropical circulation, or at least the part of the circulation that's divergent. I'll speak about that in a second. So we call that WTG. Now, pulling out a little bit of vector calculus, maybe it's called the fundamental theorem of vector calculus, but it's also called Helmholtz theorem, that if we have an arbitrary vector f, you can decompose that arbitrary vector f in terms of these operations on two scalars. One is or two potentials, sorry. One is the scalar potential, so minus the gradient of the scalar potential, and then the curl of a vector potential A. So we can do this decomposition. So if we think about our vector F here as being the wind field, then we can associate two components of that wind field, one of which, the rotational component, is non-divergent. So the non-divergent, or the rotational part, would be this curl of A, and then the other part, which is divergent, would be associated with the gradient of the scalar potential. So what the weak temperature gradient allows us to do is understand this divergent part. The rotational part is a bit more challenging, or at least at the level I'm going to present here is more challenging. So how do we kind of apply this? So let's start from the thermodynamic equations for energy and moisture. I'm not sure if I explicitly wrote these before, but essentially we can look at a kind of budget of, in this case, dry static energy, temperature essentially. I mean, we can think about that as temperature effectively. And then moisture. And so we have the left-hand side is a sum of the partial derivative of S with respect to time, plus these terms, U dot the gradient of S plus omega times the pressure derivative of S. This just comes from taking the material or total derivative of S. So you have the kind of partial derivative here giving the local time rate of change of S, plus the effect of, the fact that the atmosphere is in motion gives you these other contributions to give us what the total rate of change of S would be if we were following along with the fluid flow. So this is, in the kind of parlance of things, this would sort of be the local derivative. The whole thing here is the total derivative. One is kind of the Eulerian perspective, the other is the Lagrangian. Anyway, details. So on the left-hand side, we have that. And then on the right-hand side, we kind of have the terms you could think of as forcing the change of S the total change of S with respect to time. So convective heating, which we call Q sub C, and radiative heating. You also have kind of embedded within this convective heating would be sort of the effect of fluxes at the surface. I mean, that's kind of a detail. Radiative heating would be, again, how much radiation. This is kind of applied level by level in the atmosphere. So it's just kind of calculating the radiation out long wave and short wave at each point in the atmosphere. Then we also have a equation for moisture, essentially conservation of water vapor or conservation of moisture. So again, we have this kind of total derivative, and then we have this forcing term here, Q sub Q, which we call the convective drying. And what I'm going to do, I think I'm going to do this, maybe not in the next slide, but I'm actually going to look at these equations and do vertical integrals over them. So when you do a vertical integral over Q sub C with respect to pressure, you actually get something that you can relate to precipitation, the kind of surface precipitation rate plus the sensible heat flux. And then if you integrate over do the same integral over Q sub Q, you get minus the precipitation rate plus the evaporation or evapotranspiration. So this is expressing the effect that when we have rainfall occurring, that's giving us a heating term in equation 1. When we have rainfall occurring, that's giving us a drying term or a sink for moisture in equation 2. So let's think about the consequence of small temperature gradients, small horizontal temperature gradients in the tropics. So just rewriting the tendency equation, now isolating the local derivative of S with respect to time, we have these kind of forcing terms, or we're now moving the advection to the other side to make it look like a forcing on the local time rate of change. Do the same thing for Q. Focusing on the S equation, the dominant balance is typically this term, Q sub C and Q sub R. So we're kind of ignoring, if you think of things in kind of steady state or close to steady state, this term would be small. And if temperature gradients are small, and you know, this is the dry static energy, which also depends on the geopotential, but taking the gradient of that is 0, and if the temperature gradient is small, that term drops out. So you're kind of left with this dominant balance in the dry static energy equation. So in deep convecting region in the tropics, of these two terms on the right-hand side, the convective heating is typically dominant over the radiation. And assuming if we can make some assumption about the vertical structure of S with respect to P, so if we can think of that as if that derivative is approximately constant, then ignoring Q sub R relative to Q sub C, thinking about this as just kind of a scale factor, then Q sub C is proportional to omega. So in other words, the vertical motion field is proportional to the convective heating. And if we take the integral of the vertical integral over Q sub C, that's proportional to the precipitation. So in a sense, what this is telling us is that if we could specify the vertical velocity profile, that effectively determines the rate of precipitation. And that's kind of what we conventionally think about in the tropics, right? That you have where we see regions of intense convection in the tropics is where we tend to see regions of large-scale ascent, okay? And that's basically what I'm expressing here. So I would say that this is sort of maybe the conventional view of things. If given the vertical velocity field, then that determines the precipitation. That's kind of one way of looking at things. The kind of WTG, the kind of perspective that we'll sort of think about here is sort of the other way around. And that's to assume that if we can determine these two terms, or if we're ignoring Q sub R relative to Q sub C, then if we determine the precipitation field or the convective heating field, that effectively determines the vertical velocity field. Now, why go through this kind of exercise? Well, doing that allows us to basically have a diagnostic equation for omega, a diagnostic equation for the vertical component of the motion field, rather than a prognostic, a time-evolving equation for the dry static energy or the temperature. Now, why that's valuable to us is that if we know omega, then we can use omega and the sort of continuity equation del dot V equals 0, approximately, to actually relate the vertical motion field to the divergence of the horizontal motion field, okay? So in a sense, what the WTG equation, by kind of sacrificing this prognostic equation for dry static energy, we can sort of short circuit the need to actually look at the momentum equations. If we're only, again, this will, through the divergence relationship, will only give us the divergent part of the wind field. We still have the rotational part of the wind field that this isn't specifying, okay? You can kind of extend this framework to apply to the rotational field, but at the level I'm talking about here, we're just focusing on the divergent part. So by sacrificing our ability to know how S evolves through time, we don't have to solve the horizontal momentum equations. So that's all a bit complicated. Let me relate back to yesterday's lecture to hopefully kind of pull some of these pieces together. And so you'll remember at the end of the part one that I did yesterday, I kind of put up this schematic. And this schematic was related to, again, we were talking about convective quasi-equilibrium, but kind of focusing on different aspects. I should have actually duplicated it here. But the things kind of the things in the middle here are essentially different interpretations of convective quasi-equilibrium, at least as in this review article that I referred you to in the slides. So what I want to focus on here is this kind of interpretation of the convective quasi-equilibrium as a dynamic balance, okay? And that has this kind of arrow here to this concept called the free ride. But the free ride, which was kind of an early, the sort of earliest incarnation of this, is essentially the same as this WTG formulation, in the sense that we can start with an equation like this, okay? So let's now think about this equation, a kind of dynamic, a sort of dynamic balance equation, even though we got it from the thermodynamics, but a dynamic balance equation. And let's think about it in the context of convective quasi-equilibrium. So if we subtracted Q sub R over to the other side, then we have, something here on the left-hand side equals the convective heating Q sub C. If I, again, repeat the equations that I showed from Arakawa and Schubert, which define things in terms of this cloud work function, and associating part of the cloud work function with the production of energy by the large scale and the consumption of energy by the convective scale, we have a large scale side over here and a convective scale side over here. And in a sense, we can kind of, you could think about mapping the left-hand side here to the large scale term over here and the convective heating to the convective scale term over there. So, in a sense, maybe that way of interpreting things as a dynamic balance is consistent with convective quasi-equilibrium, at least in the sense if you kind of add this additional piece, which is due to the large scale motion. And also in the context of the first topic I talked about yesterday, radiative convective equilibrium, in the sense that we were talking about radiative convective equilibrium, this term is actually zero. There's kind of no large-scale motion term. And then you would just have the balance between the convective heating and the radiation, and what radiative convective equilibrium allows us to derive as a temperature profile that basically allows this equality to be satisfied. Okay. I just wanted to point out also, because Kathleen's talk kind of reminded me of this, we have this sort of view, and we'll talk a bit more about this tomorrow with convection parametrization, but an idea that's called convective adjustment or relaxation. That's basically, you could basically think of it as starting from this kind of convective quasi-equilibrium notion, but instead of requiring the sort of balance to hold kind of instantaneously, you kind of allow some adjustment time, and we'll talk about the complications of that. But you can essentially represent this convective heating in terms of this kind of simple formulation related to the temperature, related to the temperature of a column of the atmosphere, and some temperature which is essentially the temperature that corresponds to a neutrally buoyant profile. And so the convective heating then becomes proportional to the difference between the temperature and the kind of neutral stability. I mean, essentially that kind of maps onto the buoyancy, divided by this adjustment timescale, okay? What Kathleen showed yesterday is kind of a relationship between precipitation and column water vapor, kind of thinking about things here in a very hand-wavy way. We can think about that also being a relationship to the extent that precipitation and convective heating are related. Think about that as a relationship between convective heating and column water vapor. And something about the column water vapor is related, I mean, the details here are important, obviously, but related to the instability and the buoyancy, essentially the things that we're looking at here. But we had this scaling exponent, beta, which was 0.22 or so. So that gives us a functionally distinct relationship, right, a power law relationship. But if beta happened to be a value of 1, then you'd kind of get something here that's W minus WC, which, if that can kind of map onto this, T minus T neutral. And that the difference between this kind of behavior and the power law is here you get this time scale. Here you don't have a unique time scale. The sort of, if you think about what the units would be on precipitation, it would be something per unit time. So to kind of get a balance of units, you have to have the correct units over here. Because this is a power law, it essentially means you can't reduce to a single time scale like we're doing here. Now, I have to be a little bit careful because this time scale is something that we have to impose. We like to think maybe we understand something about the physics of convection that would allow us to specify this time scale in some reasonable way, but that turns out to be not so straightforward. So I'm almost done with the first part, so although we're technically at the break, I'll just finish the next couple of slides and then we can come back. And that's to kind of circle back to the ensotropical teleconnection and thinking about it in the context of WTG. Yep. Yep.
What would you attribute the W to, what would be a large-scale vertical motions that you diagnosed there? What would you attribute them to in the tropical atmosphere?
What would the large-scale vertical motions be?
That's your W that you have, I mean your omega that you have in the equation.
Well, I mean, it's essentially, I guess, the kind of large-scale horizontal wind, the sort of divergent component of that.
So you mean, but that would be associated with something like wave motion?
I mean, it could be wave motion.
Okay.
I mean,
the way I always think about it is that the tropical atmosphere is always sinking everywhere at all times.
Right.
The parts that really rise are the convective. So I was thinking, well, how do you actually separate the omega from the convective?
That's true. I think that's an important point. So the question was, how do you actually separate the vertical scale motion at the convective scale, this kind of subgrid scale from what I'm talking about here, which is the large scale? I don't think that's obvious. It is something that we do, but I think it's a good point. So I wanted to come back to the kind of tropical teleconnection and kind of frame it in the context of WTG, weak temperature gradient. And this kind of goes back to it's essentially what Jiang and Sobel did in their 2002 paper. What we did in this 2005 paper was just kind of replicate it in a more realistic, well, Jiang and Sobel did it in the context of what we call a single column model, where you kind of impose the forcing on the column externally. We wanted to do this in the context of a model where we're kind of doing it within the model itself, rather than doing it as kind of forcing some single column model. So we actually chose, for this particular exercise, which was more just an illustration, we actually chose a very simple model, and I'll talk about that after the break, which is this this family of quasi-equilibrium tropical circulation models, QTCM1. Essentially, with QTCM1, we did a very standard thing in this kind of in this sort of modeling world, which is to impose sea surface temperature anomalies. So we're essentially not thinking about the fully coupled ocean-atmosphere system, or at least in where we're imposing sea surface temperatures over here. We're essentially giving the atmosphere the boundary condition, okay, which is a lot different than allowing the atmosphere and the ocean to communicate, which has issues. For this particular implementation, though, we only do that sort of impose sea surface temperature or prescribed sea surface temperature over some box in the Pacific. Everywhere else, we took this model, this intermediate level complexity model, and we coupled it to a so-called slab ocean model. The oceanographer in the audience will kind of laugh at a slab ocean model, which is essentially just a finite thermal mixed layer. It doesn't have ocean dynamics. You can imagine what that might do, but it at least allows us to kind of look at the coupling between the ocean and the atmosphere, at least in a sort of crude way, in the remote tropics. And so what we did to kind of make this a WTG model is we just kind of artificially flattened out the temperature profile in the model. Now, it turns out when we did this, we could have actually done it in a more elegant way than what we actually did. So if I ever redo this, I'll do it better. But it still, I think, illustrates the point. So the comparison here is between the standard version of this model, where we haven't done this flattening of the temperature, the anomalous temperature gradient. So it's a model. It simulates things. I would argue, given the level of complexity of the model, it does a pretty reasonable job simulating what we're interested in simulating, which is, sorry for the kind of poor graphics here. We have anomalous convection and above normal precipitation, kind of where we've imposed the warming from this 97, 98 El Nino event. And then you do see this kind of suggestion, the model's producing this kind of horseshoe-shaped pattern. The model, even though it's simple, can do the sort of the kind of wave dynamics of the Gill model. I mean, in a sense, it's like the Gill model, but we just add the moist processes. And then in the remote tropics, where it's kind of gray shaded here, is where the precipitation is negative. So there's an overall tendency for negative precipitation anomalies below normal rainfall in the remote tropics. Now, you see these kind of regional scale things, but if you kind of averaged over a big box, you mostly see the negative anomalies. So that's the standard version of the model. What does the WTG version of the model do? So when we make this the weak temperature gradient version, you get the sort of pattern that you expect in the Pacific. I mean, the details are different. You also get a kind of reduction of precipitation across the remote tropics, but you'll notice that there are some interesting kind of differences that we see, which might be peculiar to this particular model. But the essential take-home message of this study was that we can kind of understand this ENSO teleconnection in the context of this WTG model. In other words, to understand at least the impact of ENSO in this part of the tropics, all we need to kind of understand is how ENSO impacts the tropospheric temperature field. The wave dynamics, I mean, obviously the wave dynamics and other things can modulate the precise details of the spatial structure of these anomalies, but you get this kind of gross tendency for negative anomalies over here balancing or anti-phased with the positive anomalies over here. So just one final point on this, because it connects to what I'll talk about on Friday. That's basically taking this WTG framework and instead of applying it in a coarse resolution model like we did in that study, is using it as a kind of boundary condition, a way of parametrizing the interaction between convective and large scales in a model, the weather research and forecasting model WRF, which some of you are familiar with, I'm sure, run as a so-called cloud resolving model. So a model in which we don't have to do convective parametrization in the way that we'll talk about tomorrow. So presumably, you can argue with this, Dave would argue with this, but would give us maybe a more accurate representation of what's going on because we're more explicitly representing the physics of convection. Now we still have to treat the microphysics and other things in, maybe the not most physical way or a parametrized way, but we can at least get closer to resolving the convection in this type of model. And so there's a nice study that was published late last year by Usama Anbar, Adam Sobel, and colleagues, kind of applying this WTG framework in the context of this cloud resolving model, sort of the first time this has been done, and using that over a domain in the Amazon, where, for those of you who keep up with the Amazon, there was a nice observational campaign that just wrapped up called the Green Ocean, Kathleen mentioned it, the Green Ocean Amazon campaign. So kind of using this sort of modeling framework to leverage on those data, as well as Dave's dense network from the central Amazon. But I think we can do a lot with this kind of modeling framework in the Amazon. So I think with that, I'll stop. We can take a break and then reconvene. Yeah, I have to think.
También estoy representando a estas alturas, la dimensión de las partículas naturales. Luego te pasas por mi currículum y te muestro.
I think we'll go ahead and get started, maybe?
Lo que a él me escribí, a mí no me contesta, pero él está por
I need some muscle over there to...
y digo, si ella me puede dar la si ella me
They look like they're engaged in science, though, so I hate to interrupt them.
That doesn't happen very often with Carlos, so you have to let him go.
Yeah. So, welcome back. Maybe we lost a few people because they didn't want to do the assignment. Be working on your assignment. So, I wanted to, for the second part of this lecture, or second half of today, talk about a kind of modeling framework, which I introduced, the quasi-equilibrium tropical circulation model, or QTCM, kind of give you an overview of this model, and in part to do this because, I think especially maybe for the students out there, you can download this model, you can set it up and run it, and it's fairly quick to do that. You can, with your computer skills, do it within minutes. I did it in an afternoon, so you can set it up yourself, and it's easy to play around with things. I have another version of the model. If you're more ambitious and you want to look at that one, you can email me, and I'll be happy to have someone work with that version. But what is QTCM? Or I should say, what are QTCMs? Because they're really a family. You can think of them as a family of models. Well, it's a type of model, a type of modeling framework called an intermediate level complexity model. Or sometimes they're called what are they called? Models of intermediate level complexity. And this particular type of intermediate level complexity model was designed by David Nealon's group at UCLA, so I worked in Nealon's group, so in part that's why I'm talking about it, because I've worked with this particular model. But I think it's really a kind of nice tool to work with, subject to the sort of constraints, obviously, that come along with running a model of this type. So what's the sort of relevant theory? And I'll talk a little bit more about this, but it's basically to take approximately correct analytic solutions, at least within the constraints of convective quasi-equilibrium, and use those to basically pre-solve the vertical structure of the atmosphere in tropical deep convecting regions, and then kind of apply that structure elsewhere in the tropics. Now, why would you want to do this? Well, this model was developed, as you can see from the two citations there, way back in 2000. And it turns out by doing this kind of predetermination of the vertical structure, you can actually make the model run really quickly. And maybe it's not so much of an issue anymore because, you have probably more computing power on your cell phone than what we had with desktop computers at the time this was made. But it made it computationally efficient. Just because it's, in 2000 wasn't that long ago, but let's just say just because it's old doesn't mean it's not something we should still play around with. I think it still can be used to do useful things. So the implementation, as I'll describe, is to take the primitive equations, basically our equations, Navier-Stokes equations plus the thermodynamic equation, water vapor equation, and project those equations onto these analytic vertical structures using a type of expansion. It's basically what you do sort of in linear algebra when you have a set of basis functions and you project some, like if you have sines and cosines as a set of basis functions, you can decompose an arbitrary, at least a well-behaved function in terms of a sum of sines and cosines. It's essentially the same process here. So the idea kind of in a nutshell in this blue box is that convective quasi-equilibrium that we talked about constrains temperature. By constraining temperature, that tells us something about the vertical structure of baroclinic pressure gradients. Baroclinic pressure gradients constrain the vertical structure of the horizontal winds, and that in turn constrains the vertical structure of the vertical component of the winds. So sort of flowing from convective quasi-equilibrium, we can kind of derive these analytic structures, or David and Ning Zheng derived them for these other, for the momentum fields. Now, it turns out this doesn't say anything about the moisture field. The moisture field isn't constrained in the same way, so then we just kind of use, a reasonable looking basis function based on our sort of observed understanding of the moisture profile in the tropics, but that might be an issue. QTCM, as kind of a family of models, includes the full complement of GCM, I'll say GCM-like parameterization. So just like a global climate model, it has things like radiative transfer, surface turbulent exchange. It has a convection parameterization called the Betts and Miller scheme. I'll talk more about that tomorrow. These parameterizations aren't as complex as what you might find in the GFDL model or the NCAR model, but it's essentially in the same spirit in this model. As I mentioned, QTCM is computationally efficient, so maybe not as important anymore today, but still. And also, it's now been applied to an array of problems. Some of these are things I've done, but certainly other people, obviously other people. We've looked at the ENSO teleconnections, monsoons, global warming, and there are other things I think that we could still look at with this type of framework. So the primitive equations and this process for doing the vertical expansion. So we can essentially write the primitive equations. We've already seen the temperature and moisture equations. This is just in a different form. But we have on the left-hand side the total derivative of the temperature or the dry static energy. And that's equal to these diabatic terms on the right-hand side, the convective heating radiation. But the radiation is now split up into short wave and long wave, and a sort of turbulent exchange, the last term on the right-hand side, which is where essentially when we do the integral over the vertical, that term becomes the sensible heat flux. Same thing for moisture. Again, the left-hand side, the total derivative of Q, the specific humidity, and then the forcing on the right-hand side in terms of Q sub Q plus this vertical, this turbulent exchange of moisture. And then we have the horizontal momentum equation, just for completeness, or I should say the horizontal momentum equations. There are two of them. It's a vector equation, so it's just Navier-Stokes. And then the continuity equation, which relates the divergence of the horizontal component of the winds to the vertical component. So what we do in terms of the procedure is a vertical expansion. So I'm illustrating here, the temperature projection. So we take these equations and we basically have some, should be using the pointer, we have some temperature, we have the temperature field, which is what we want to solve for. And we basically write the temperature field in terms of some reference temperature profile, which is just a function of pressure, so there's no dependence on time, latitude, or longitude. And then we have this sum of terms, which consists of a part we call T sub k, which depends on x, y, and t, latitude or longitude, latitude, and time, but then multiplied by some vertical structure function, a sub k. And you'll notice there's a sum here, k equals 1 to capital K. We can do this vertical expansion over a large, as many of these basis functions as we want, as long as we can define them in some reasonable way. What I'll be talking about mostly in this presentation is just going to be QTCM1. So it's QTCM1 because it just has k equals 1. So it's just the reference plus the first term. And then the velocity projection, basically taking the velocity field and using the vertical structure of temperature, which we'll talk about, constraining the velocity profile that we're basically projecting onto. So we have the velocity, again, which appears here in this horizontal momentum equation, function of x, y, pressure, and time, which we'll write as this coefficient v of p, which contains the pressure dependence, times the field that depends on longitude, latitude, and time. So by doing this expansion, plugging it into these equations, or everywhere you have a temperature, you'd replace by the expansion. Everywhere you'd have a vector v, you'd replace by this. We do the same thing for moisture as well. So we basically then have equations here that we vertically integrate. And when we vertically integrate, we're basically integrating, of course, over the pressure dependence. By vertically integrating, we vertically integrate these terms. And what it allows us to do, for example, in the radiative transfer, is we only have to really do the radiative transfer calculation one time. We just do it sort of at the initial start of the model, and then that kind of reduces, these radiative terms can be written in a very simple form. I mean, it's a kind of linearized model. The computational efficiency part kind of comes in this step. In a GCM, a global climate model, a lot of the model kind of computational time is spent doing radiative transfer. Because if you remember back to, when we were talking about radiative convective equilibrium, you have an atmosphere that consists of a mix of stuff, and really the radiative transfer is happening because of the atomic properties of the constituents in the atmosphere. So you kind of have to do a line-by-line, what's called a line-by-line calculation, do that everywhere in the vertical. The model spends a lot of time doing that. This model, by kind of doing that step up front, really becomes computationally efficient. But again, that's maybe not so important anymore. So what are the basis functions? What are the functions that we choose to do this vertical projection, or what were chosen to do this vertical projection? So these are all relative. Remember, there's in the temperature profile, there's this reference piece. That's basically something we just give to the model. And that was based on looking at a kind of reference sounding in the Western Pacific, kind of a canonical sounding, if you will. And from that canonical sounding kind of derived this sort of what's called the first baroclinic mode of temperature, which is basically this. So the A1 here would be the structure of this function A sub 1 of P, so that's how it depends on pressure. So it actually increases as you go up. The baroclinic, so the sort of baroclinic part of the momentum and the barotropic part, of course the barotropic part doesn't depend on pressure, so that's just basically an offset. And then you have the kind of baroclinic mode that's consistent with this temperature, kind of using the hydrostatic or hypsometric relationship to kind of get this. These two are related. And the vertical velocity, once we know this vertical structure of the horizontal winds, that kind of gives us a vertical velocity profile. The moisture part is the one that really isn't constrained by this process. So actually in kind of the development of the model as kind of a test, different vertical structures for moisture were chosen. There is sensitivity to it. That's actually something I'll come back to. But to leading order, as long as you kind of have a vertical structure that looks like this, and that's kind of consistent with the vertical structure of specific humidity like Kathleen was showing. It's higher near the surface and it decreases with height. Again, in a mean sense. I mean, you might have obviously local variations from that, but this is all sort of building based on some kind of mean profiles. So the applicability of this kind of basis function, so really what we're doing is we're taking this kind of basis function and we're basically saying we can apply it anywhere in the tropics. So in the, sort of by nature of where the sounding was chosen in the Western Pacific, that's a pretty intensely convecting region. And so in the convective region, the temperature in a sense that the model is calculating is pretty close to this kind of reference, what we're kind of giving it as the profile. As you move away from the deep convecting region, you might actually get into a place kind of adjacent to it where you start to develop temperature gradients that are not negligible, in which case the sort of real profile of temperature at that point might be like this wiggly curve, and this is what the model kind of says it should be. And then in the, kind of far away from the convecting region, you might have quite a bit different structure because it's not, the model is kind of limited in the vertical degrees of freedom, and it might not be so representative in this region. The Nealon and Zhang paper that kind of goes through the development, I think, does a nice job of arguing why this might not be so critical, at least in terms of using QTCM, and that's kind of maybe an important point to make. That's maybe a more general point. you should, always think about when you're choosing a model to do a problem, is that model appropriate for the problem? So QTCM is designed to do certain problems. In particular, it was designed to do the ENSO teleconnection problem. So in the context of the ENSO teleconnection problem, maybe this kind of thing isn't that important. But if you wanted to look at other problems, this model may not be appropriate. So just to kind of, without really going through too much in terms of the results of this model, because I want to talk about something that kind of came after it, looking at the precipitation field averaged over DJF from a satellite product CMAP and comparing it to what the model simulates the precipitation field should be, if you're a pessimist, you're going to look at this and say, well, that looks terrible. If you're an optimist, you'll say, well, okay, we see these regions of strong, deep convection. Here's my, I like the South Pacific convergence zone. Well, the model has something that looks kind of like that. South Atlantic convergence zone, the model has something that kind of looks like that. You get, kind of this band of convection, sort of an ITCZ, if you will, over the Indian Ocean, maybe not in quite the right place, but it's there. Over the kind of Congo Basin rainforest, you see a precipitation maximum. Even if you're an optimist, because you're a scientist, you're also pessimistic or skeptical. And so you look at this and say, well, there's some things it's clearly not doing right. So look at the intertropical convergence zone in the Pacific. Model has a hard time making an ITCZ. Just, it can kind of do these more blobby, blobby being a scientific term, but these more blobby, less linear, narrow features like the South Pacific convergence zone has a harder time doing the sort of ITCZ, and I'll talk about maybe why that's the case. No ITCZ in the Atlantic. Interestingly, in a sense, the model is, the T, remember, stands for tropical. The model is run over a domain not all the way to the poles for, reasons of stability, but it does include higher latitudes. And actually, the model generates things that look kind of like storm tracks. You have a storm track here in the Pacific and a storm track in the Atlantic. Model wasn't designed to do the higher latitudes, but it has baroclinic instability. If you look at the sort of transients that the model produces, they look kind of like storms in the mid-latitudes. This model, I'm trying to remember, you can run it at very high resolution if you want, but if you run it at, say, equivalent to 2 degrees longitude by 2 degrees latitude, that's enough to resolve the sort of synoptic scale that's basically giving you the storm tracks at higher latitudes. The model can do that. And obviously, the details, I wouldn't want to use this model to kind of study the dynamics of extratropical circulations, but it still has the right kind of flavor, okay? The model also has a tendency, if you'll kind of look at the magnitudes here, it has a tendency to really maybe not so much in this kind of picture for South America, but much too intense rainfall over Africa. So that's kind of a common feature of this QTCM1 and something that we had hoped to correct with another version, which I'll hopefully get to at the end. The short answer to that is we haven't really corrected it, despite trying. So convective margins is kind of the next thing I want to talk about. And this, it seems like maybe I'm switching gears, but it is kind of related. It's related to what I was talking about just now with QTCM, because the sort of framework of QTCM, thinking of it not just as a model, but kind of a theoretical construct, kind of provides the way that we kind of looked at this problem. So what do I mean by, or let me just, the style of this has changed because I kind of plagiarized myself and took these slides from a previous presentation, so apologies for the different style, but the research that's kind of motivated